In this second video, I want to talk about how we do thresholding. Not just, whether it's corrected or uncorrected, but how we interpret the thresholds that we have. And one of the things that you find frequently in experiments is this idea that in one condition, something is significant, and in one condition, it's not significant. And therefore, the two are obviously different because one was significant and one wasn't. And you see this all the time, right? This is a quote from a paper from Nieuwenhuis. So not only can I not pronounce French names, I can't pronounce Dutch names. I'm sorry, I'm terminally American, and I just got to apologize. So my apologies if I'm butchering their names. But this is a great study, great paper in Nature Neuroscience. And the quote they used was, the percentage of neurons showing cue-related activity increased with training in the mutant mice, and that was significant, but not in the control mice, where it wasn't significant, right? And the implicit assumption here is, well, training works in the mutants, but not in the control mice. So there's a difference between those two conditions. You could argue that that's what I said. And if you were to plot that in terms of the effect sizes, you're kind of expecting something like this. Group 1 is our mutant mice, where there's a big effect. And then group 2 is our control mice, where there's basically no effect. Because in the one case, it's significant. You can see that on the left. And on the other case, it's not significant. You can see that on the right. Right, big difference. And if you saw that plot, in addition to that sentence, you'd probably go, yeah, okay, fair enough. However, this plot is also consistent with that sentence. So in this case, the group 1 mutant mice on the left is significant because it's just slightly above chance, which is 50%. On the other hand, the group 2 plot is not significant because it's slightly below chance at 50%, right? However, is there a difference between these two plots? Probably not, right? Because the error bars suggest that they overlap. So that is to say, one is a significant effect, one is a non-significant effect, but that doesn't mean the two are different from one another. And if what you're interested in is, are these two conditions different, then it's critical that you test for that. Otherwise, you're engaging in what's called a thresholding fallacy. One passed the threshold, one didn't, and we're going to assume that that means that the two are different from one another. But if you're interested in whether they're different, you have to test whether they're different from one another. And that is not saying one did and one didn't pass a threshold. Right, so this is the threshold shown here at chance, and you can see that one passes and one doesn't, and therefore you can get the same data that are consistent with that sentence, but a very different interpretation of what it actually means. So, you get this whenever you have a group or condition that shows a significant effect while the other group or condition does not show a significant difference. And this kind of gets us to that famous quote, surely God loves the 0.06 nearly as much as the 0.05. By choosing 0.05 as our significance threshold, we've made an arbitrary decision. It's a group decision. We do it as a heuristic across fields, so we tend to think that it's meaningful, but it's not. I mean, is it really critical that it's one chance out of, or 5 chances out of 100, let's say, instead of 6 chances out of 100? Do you think that that makes a huge amount of difference? If not, then the example that I just showed you is highly relevant, because if you had accepted 0.06 as your criteria instead of 0.05, well then both of them, both of them are significant, and you get a completely different interpretation of the exact same data. So the thresholding issue is that we've arbitrarily put a nonlinear threshold on this. That is to say, it passes or it doesn't. And if it passes, we're going to treat it as meaningful, and if it doesn't, we're going to treat it as not meaningful. That's fine for the individual thing, but that doesn't mean that when you compare the two conditions or the two groups directly, those are different from one another. What you need to do is actually test that difference. And there are multiple ways of doing it. It could be that you use a 2-sample test where you test group 1 against group 2 directly. Or it could be that if you have some sort of more complicated design, like the example that I talked about, you would look for an interaction, because there were two groups, the mutant mice and the control mice, but then there was also another condition that was before and after training, and it was the effect of training on the different groups. So that, in that case, you're looking for an interaction term rather than a simple paired 2-sample t-test. Of course, you might argue, oh yeah, sure. Some areas of neuroscience may make thresholding fallacies, but surely not imaging, right? Well, here's an example from exactly the same form, right? Training significantly decreased Broca's area activation for words, significantly, but not for pseudowords, where it was non-significant. And here you get to see a picture of activation in Broca's area, and you think, yeah, sure, there's a big difference between what happens when you train words and non-words. And this is that sort of interaction thing, because again, we have two conditions. We have two factors. We have words and non-words, and we also have pre and post training. So for instance, if you look at pre-training and for words and pseudowords, they're basically equal. There's the white bars there. But after training, there's a reduction for the activation for words, but not a significant reduction for pseudowords. So again, if you saw this plot, you would say, yeah, that interpretation is reasonable, that words and pseudowords are responding differently to training. However, without that plot, if all you had was that sentence, this is equally possible, right? Where this difference between pre-training and post-training for words is just slightly bigger and enough to get over that statistical threshold and make it significant than the difference between training for pseudowords pre and post, where the effect is just ever so slightly smaller, but that means that it's not sufficient to cross over this threshold, and therefore in one case it's significant, one it's not, and you'd say, then there's a big difference between what training does for words and non-words. And then you look at this plot and think, hey, wait a second, they pretty much look the same to me. In other words, this is the thresholding fallacy, and it's a very, very easy one for any of us to fall into. The key thing here is if you're trying to report that there's a difference between two groups or two conditions, then you need to test for that difference directly. That could be a paired t-test, it could be due to an interaction, but one way or another, it needs to be tested statistically in order to claim that there's a difference. You have the data, there's no reason not to test for it. The other thing that I want to point out here, that's presumably obvious, is by plotting the effect sizes, regardless of what they are, you can see this rather clearly. And this is yet again an illustration of why it's so important to plot your effect sizes. You may sort of see that one condition is significant and the other isn't, and think, oh yeah, definitely there's a difference, because maybe that's what you expected. But then all of a sudden you plot them and realize that you're in a situation like what we see here on the screen, and think, oh, wait, that's not what I thought at all. How did that come about? Oh, right, I need to make sure that I test for that difference explicitly. So this is an important point. It comes up all the time. One of the things that frequently comes up with is laterality differences. So people look at their activations and say, oh, look, there's more activation on the left than there is on the right. So there's some sort of difference in terms of what's happening between the left and the right. Well, maybe, but if that's what's important, if that's the claim that you're making, then it's really critical that you test the difference between left and right. You can't just look at it and say, well, there are more voxels that pass threshold on the left than there are voxels that pass threshold on the right, because at that point you've made the thresholding fallacy. So it is a particularly common one. It's easy to avoid, but it happens to all of us. As soon as you plot your effects, regardless of how they're generated, then you can normally see that you're in this situation and then correct it by doing the appropriate statistical test.